Good day, this is Dr. Ali Mugable. Today's topic is matched filters. We will give some examples in baseband transmission, but the concept remains valid. So we'll focus on matched filter. The outline of and objectives will, as I mentioned, we'll focus on baseband pulse transmission as an example. We'll look at the dispersive channel, and then we'll focus on matched filter. Properties of the matched filters, and match filters for rectangular pulses as an example. So let's just lay the background for baseband pulse transmission and ISI. In transmission of digital data over baseband channels, the digital data has significantly low bass, low frequency content. And to allow this signal to pass, we require low bass channel or baseband channel with bandwidth large enough to accommodate the signal, large enough to accommodate the essential frequency content. What if this channel is not wide enough? If the channel is not wide enough, we will get what we call dispersion. So we'll have baseband channel dispersion. The meaning of dispersion is that the signal will disperse in time. The signal that was limited to a given time duration, TB, or bit duration, will cover more time. It will be dispersed. So the frequency response of the channel is not an ideal low pass filter, and there is going to be frequency variation. And even if we assume it's a low pass filter ideal, then the bandwidth limitation will also affect the output signal. So the received pulse will be affected by adjacent pulses. So it's not going to take the time duration given to it, it will disperse, expand. As we can see here that I'm representing the bits with the following shape, whether we have positive and negative, but because of dispersion, every bit is expanding into the next and affecting the adjacent symbols. This is known as inter-symbol interference. So basically in communication, we have a problem with digital communication called inter-symbol interference. You cannot just send these square pulses and receive square pulses because rect has a frequency representation of sync and it covers the entire frequency band. So this cannot be transmitted over a band limited channel. So we can summarize that dispersive baseband channel is a major source of bit errors. So somebody would like to say that why don't we just send more data or higher data rate? Higher data rate means we have shorter pulse duration, which translates into wider bandwidth requirement, and then we will suffer more of ISI. So we can think of ISI as a result of bandwidth limitation, and it's really the limiting factor for not having more higher data rate in digital communication. So dispersive baseband channels is a major source of bit errors. So now we can summarize that we have two problems. We have noise and we have ISI. So how can we correct and control ISI? We can use, for example, equalization or pulse shaping. So we are laying the ground that in order to receive the bit correctly, it's just not noise only. We have noise and bandwidth limitation. But we can say that ideally, the effect of ISI can be controlled, can be reduced to a small limit by using proper pulse shaping or equalization, and these topics are covered in other videos. For now, we know that there is a problem called ISI. Now, the source of bit error in baseband communication or transmission is either ISI or channel noise. As I mentioned, we will study them separately, and then we can have a better understanding. So let's start by looking at noise, assuming that there is no ISI. We have two examples here. The upper one is a high signal to noise ratio example. A high signal to noise ratio means that the noise relative to the signal is small, or the signal relative to the noise is high. The noise power, of course. Now, if you add the two, assuming as if noise, you get this signal. Although there is some noise, we can still make perfect judgment or decision whether this is positive or negative or positive. So we can end up without errors, and we call this high signal to noise ratio. The problem is more dramatic if we have low signal to noise ratio, and in that case, the amount of power in the signal relative to the noise is low. Imagine if you add the two together, you'll get the following curve, and we get noise. And we can make a wrong decision like here, we can get positive part. So the question in hand, what is the optimum way of making decision? And that's a valid question. We cannot just sample at the middle. We cannot just count the peaks. We cannot just find other options. There must be an optimum way of making decision. So this slide summarizes the problem. How do we make decision in the presence of noise? So the answer to this question is the matched filter. The matched filter is the optimum detection of pulse or a known waveform, whether it's pulse or any other shape. It should be just known to the receiver in the presence in additive white noise. And we'll see that in details. But for now, we are jumping to conclusion that whatever makes an optimum detection for pulses in the presence of additive white noise is called the matched filter. The matched filter is a linear time invariant system where impulse response is matched to the pulse signal. And this is why the name is called matched filter. We'll see this in more details. We're just now defining the name to be matched filter because h of t, or the impulse response, is matched to the waveform used to represent the symbols. Remember that here we assume that the major limitation of the communication system is not ISI, it is the noise. The following two diagrams shows you two possible examples of pulse shaping, including the unipolar on-off or the polar. And our job in the presence of noise is to find the optimal solution, which is the match filter, and it should have an impulse response similar to the original waveform. Now we look at the following example where we have a signal g of t. I am representing the signal with green color. The noise is the red part of the problem, and then we have the resultant curve here is g of t, which is nothing but the sum of the two. We will assume that there's a block here, block diagram, a linear time invariant impulse response or system h of t, shown in purple, and we'd like to have this to get the optimum decision. So our objective is to design a receiver, that's the receiver, that detects the pulse of g of t in an optimum way where the given is the corrupted signal with noise, the blue signal. Or alternatively, our objective is to minimize the effect of noise at the output of the filter. We'll spend some time showing that this is really a matched filter. So at the receiver, we would like to recover the decision. Remember, in digital communication, we have a sampler here, because all we need is making a decision in every t, capital T bit duration or symbol duration. So we're saying at the receiver, recovering the shape of the transmitted pulse is not important. I don't care about getting exactly the original waveform. All I want to know is to make a decision which pulse was transmitted, positive or negative, and that's called a detection problem. So the filter input x of t is composed of two parts, as we mentioned, and we would like to design this optimal filter. We will assume in our analysis that this noise is zero mean with power spectral density in naught over 2. It's additive because we are adding here. It's additive white noise. So all the analysis will be valid only in the presence of additive white noise with zero mean and power spectral density equal to n naught over 2. Okay, so that's the mathematical representation of what just we mentioned here. I have the MATLAB code. Of course, those figures were generated using MATLAB by using the square wave and then adding around n noise to the sequence. Okay, so let's proceed about the matched filter. We mentioned here that the filter H is linear, so we can say that the Y, which is the output of the filter, is made of two things. It's made of N, which is the modified noise. Remember that the input noise is W. But now at the output, because of linearity, we can look at the output separately here. And the input signal G will be at the output G out, G sub O, the output. So how do we get the output signal? By convolution. So it's the convolution of the input signal convolved with H. Makes sense. Of course, we said that N in red now is the noise at the output, which is nothing but the filtered noise. And G sub out, sub O is the output signal component. We can also say that because we only take the samples at the output, I will remove T and look at capital T. So we're looking at one value. The output value at capital T equal to G naught at T plus the noise. So what is in this equation compared with that equation is just replacing small t with capital T. The objective is to find H that maximizes the instantaneous, because we are looking at one instant in time, power in output signal to noise ratio. So if you write the output signal to noise ratio, the part of the signal, the part that's positive, that's green, is G out at T. Because we're looking at power, I'll look at that square, because it's a constant value or single value, I'll just square it. And also for the noise, the output noise is nothing but the expected value of N naught. And of course, we look at the expectation of this value because it changes with time. Now that's your original signal. That's not random, and that's a random here, and this is why we have expectation. So we can summarize our, let's say, spoken objective by this mathematical notation. Eta is the outcome to be optimized, maximized, and it's given by the following expression. So we have two parts, part of which is the signal and part which is the noise. I will take this equation and proceed in the next slide. All right, so that's to recall, to design H of t such that this is maximized. I can say in the frequency domain notation, using frequency domain notation, that G out is GF, the transfer function, the input signal multiplied by H of f. So this now is the same figure, but I'm using the frequency notations here. So we can say also that the output is the inverse Fourier transform of the multiplication. Remember that G out is given by this. So if you want the output in time, it's going to be the inverse Fourier transform. That's the equation of the inverse Fourier transform. And you are only interested in the power, so will be the magnitude of the square of this evaluated at t. Okay, so this equation is representing the numerator. To find the denominator, recall that the power spectral density of the noise is given by the following expression. Remember, we had this when we have transfer over a linear system. So the output power spectral density will be the input power spectral density multiplied by the following. And we can say that the expected value of the noise power at the output is the following expression. It's going to be N naught over 2 multiplied by this. So we have some expression for the numerator, and we have expression for the denominator. We're saying that the noise output power depends on the system, H. Remember that our objective is to find H. So I will take this here, substitute, and take this guy, substitute in the denominator. So if we write the entire expression after substitution, I would like to maximize this. So if there is H at the denominator and H at the numerator, and is there a way to somehow simplify? There is square here. Is there a way to make this simpler? We need to visit the mathematicians and ask them for some help. Can we split this? Can we find a solution? And the answer is in the next slide. Okay, so for a given G, find the transfer function of H that maximizes this. There is a special formula that we need to introduce, and we will use it in our coming presentation. Okay, so this equation is called, or this inequality is known as Schwarz inequality, and we'll just explain it. We'll take a detour, and then we will utilize it here. Schwarz inequality says that if for two complex functions, complex in general, I'm using colors here, phi 1 and phi 2, and the real variable t, and if both of them have finite energy, this is a condition for the inequality to be true. Finite energy means that if you take the area under the square of the signal, you get less than infinity. And that's no problem for us in real life. So if that's the case, according to Schwarz inequality, you can find the square of the product of the integration, and you can split it into the individual integrations. And the right-hand side will be always greater than or less than the following left-hand side. And it's going to hold it's going to be equal with equality if one of the function is the complex conjugate of the other one. Of course, or a scaling factor. So if phi1 equal to k times the conjugate of phi2, then this is going to hold with equality. I can just split this integration into two integrations, where we just mentioned that k is a constant. So what is in this slide is just explaining Schwarz inequality. I will use it next. I will go back to my slides and use it in the proof. All right, now let's apply Schwarz inequality to find the optimum filter, which is called the matched filter. Now we know that I will just state the conclusions here and then I'll get back to them through the derivation. Remember Schwarz inequality, we will let phi1 equal to h of f and phi2 will be gf times the exponential. So if you go back to the expression, you'll find out that we can write the following inequality. Again, I'm using colors here to help you identify. So the red part and the green part. Now, this is always going to be less than or equal to the multiplication of the individual integrations. Now note here that I dropped the exponential magnitude because once we split them, the exponential will give you a magnitude equal to 1. It's just a phase shift. Now this inequality will hold with equality only if h of f equal to the constant times the conjugate of the other part. Only if phi1 equal to constant times phi, the conjugate of phi2. Here we don't have phi1 and phi2. We have h of f equal to constant. So the transfer function of the optimum filter should be related to the pulse shape. Fantastic. So the peak signal to noise ratio, the maximum value, is when this inequality holds. So now I can say that the peak signal to noise ratio, which is given by the following expression from previous slides, we can split the numerator into two parts like this. This is always going to be less than or equal. We can drop the h of f here and it becomes 2 over n naught, the following expression. So we can say that the peak pulse signal to noise ratio is given as 2 divided by n naught times the area under gf squared. So in summary, the optimal filter that gives you the maximum signal to noise ratio is when your transfer function equal to k times the complex conjugate of the transfer function of the signal with a phase shift. And we also know the maximum signal to noise ratio in terms of value. Don't worry, we're going to make this look simple, but I am putting them in the box as our current conclusion in the frequency domain. So note that h of f does not depend on the exact details of h of f, but rather it depends on the energy, because remember that from the power spectral density, if you take the area under the square of the signal, you get the energy of the signal in frequency domain. So the maximum value is also given by the following expression as we just mentioned. So keep this in your mind. We'll also look at them in time domain. Now to get you the impulse response of the matched filter, we just gave you the frequency domain. So I will start from the frequency domain. That's the optimal transfer function. If you do the inverse Fourier transform, I'll get this expression here. Okay, substituted. I just substitute this expression multiplied by the exponential to get the inverse Fourier transform. That's the time domain. You notice that after the multiplication, we can join the two exponents. We get the following expression. Now, for all real signals, we know that if it is a real signal, we can write the following identity, because we know that we have complex conjugate symmetry. And I can now write, instead of conjugate, as g of minus f. If you now apply the inverse Fourier transform and change variable, this is nothing but g of t in time, and this exponential result in time shift and scaling factor of k. So the impulse response of the optimal filter will have a response that's equal to the signal itself, or the waveform, or the pulse shape, inverted and shifted and scaled. And I'm writing this here as a summary. If you want to go back and look at the signal which is in frequency domain. So we can say that this is nothing but the time reverse delayed, time reverse because of the minus sign, delayed by t signal or input signal, and it's matched to the input signal because it has the same shape. Of course, we have some scaling factor. The assumption that it is made for all of this is that we have noise that is stationary and white, zero mean, with power spectral density of n naught over 2. Now, this is the filter itself. We can think of the value that we have before. So if you look at the maximum, the output value at the sampling instant is equal to 2 over n naught times the integration. Now, using Parsifal's theorem or Rayleigh theorem, we can say that the spectrum is also giving you 2 in E over n naught. To show that the spectrum of the signal is g of t, to show that this is true, I can prove that to you through the following quick derivation. The output spectrum is the result of the multiplication in frequency domain of the optimum filter times the input signal. And of course, the optimum signal is designed to be optimal, which is matched filter. So this is the expression for the matched filter. Now, g of f times g of f conjugate give you the magnitude squared. And if you look at the time domain, so you'll do the inverse Fourier transform of this expression. As we have seen that this is equal to k times g of f, and that's nothing but the energy of the signal. So the optimal value is a scaling factor times the energy of the signal. So whether you do it in time or frequency using Parsifal theorem or Rayleigh energy theorem, this is the energy of the signal and this is the energy of the signal. So this is the output, the match filter maximum signal to noise ratio. We can say it's k times E. That's the output value in value. And of course, if you look at the signal of the noise power at the output of the filter, it's the input white noise, and we have the filter squared. Remember when you spoke about going through a linear time invariant filter? Now, the optimal filter has a given transfer function, and the result of the noise will get n naught over 2, but scaled by k squared and multiplied by E because of the filter shape. So the energy of the noise is k squared n naught times E divided by 2. If you want now the signal to noise ratio, you'll get the square of the signal output divided by the expected value of the noise. And we have squared here, k squared with E squared. I'll take everything here and substitute. So you can see the arrows, how things are developed. Now we'll cancel the k squared with the k squared. And what remains here, E squared with E. We have E here, and then the two factors. So this is just to prove to you that in different ways that we will get the maximum value of 2E over n naught. The maximum possible value is proportional to the energy. That makes sense. And it's inversely proportional to the noise. That also makes sense. Or the power spectral density of the noise. So the output depends on the energy at g of t, not the exact details of the shape. If you want to use square, rectangle, what matters is how much energy is in the signal. All signals with the same energy are equally effective, of course, for the given assumption that we have additive white Gaussian noise or additive white noise with zero mean. Fantastic. Now, if you look at one example, first example, design a matched filter for a rectangle pulse. What is the impulse response of the optimal filter? Remember that the energy is the area under the square of the curve. So the energy here is a squared times t. Square of the curve is a squared. And if you want to find the area, you integrate, I get to multiply the height a squared by t. Now, if you want, you have the matched filter, which is a scaled version of the signal, flipped and shifted. Luckily, this is going to look the same. But what we did, in fact, we first flipped the signal, okay, like this. This becomes minus t, right? And then we shift it by t, so it goes back to this direction. It goes back to the same way. We have a scaling factor of k. That's a matched filter. That's a filter whose impulse response is given by this will give you the optimal decision. Now, if this signal goes through the filter without any noise, this is how the output would look like. It's a convolution. And you know that the top value, the maximum value, should equal to the energy scaled by k. So we know exactly, and this will occur at the sampling instant of t. We take only one value here and we would like to maximize it. Those values will not contribute to the decision in ideal conditions. Now the maximum value of the output signal is k times a squared times t, which occurs at t equal to t. The maximum of output signal equal to the energy of the input signal scaled by k. Okay, fantastic. Now moving to example 2, and this is really a special case. We are saying here, in case that your signal is a rectangle pulse, there is no need to look at matched filter and complicate things because your signal is constant. It's a rectangle pulse. So we can do just direct integration because we are multiplying by constant. So we can just do direct integration and take the value. We measure the area. This circuit is called integrate and dump. You just do the integration and dump the value. So this is how it looks with the area. It's going to increase and it will give you the maximum at t. The output will be a times t. We will do the decision at the peak value. Now note that this is very similar, optimal like the matched filter, but you have to be careful because you have to sample at the right time. If you exceed the time, you will not get the right answer. A third example, matched filter. Design a matched filter for the following signal. Remember that a matched filter would like to sketch the matched filter impulse response. First, we flip the signal, so we get something like this. And then we shift the signal. So we get something like this. Okay, so this is the signal shifted and scaled. So this signal is shifted to the right, and then we got the following signal. So the output of the expression is given by the following. This is this is the convolution of the two signals. Note that you need to know how to do convolution. You need to go through the different areas where we have similar overlap, negative overlap, and then we continue with the convolution. So it goes negative, then positive, then negative, then 0 again. If you are not sure how to do graphical convolution, I advise you to visit our video in graphical convolution, doing graphical convolution. You can search for Muqabil on YouTube, MUQAIBL, and graphical convolution. And also note that the maximum here is equal to the square of the energy. Equal to the energy of the signal. So we have a squared over 2, it will be a squared over 4. So this is just a constant, whether positive or negative. We look at the square of the signal. So this would be a squared divided by 4. And the duration is t. So it would be a squared divided by 4 times t. We could have added a scaling factor here, k, in all the sketches. Now this is the MATLAB simulation that I have done for you to show the real problem here. That these are the signal without noise. This is the signal without noise. If you like the matched filter or the original signal, we're sending sinusoid. That's the signal when it's going through noise, the noisy output. And here we can see that the other response, the noise response at the receiver, and we can see that it's very hard to make a decision. But once you go through the matched filter, you look for the signal of interest and you get the following response. You need to take the reading at the proper timing. Similarly, here we have another signal, which is kind of frequency shift. It changes frequency. This is the waveform that we select. This is the waveform that we select. If it is buried in noise, we get something like this. It's not easy to make a decision where exactly is the output and how many of them do we have. So once we do correlation, once we do go through the matched filter, the output tells you exactly where the signal is in time, the maximum value. You can see that we have similarity here, but it's less. Similarly here, it shows you that there are two signals, two multipath components that are received. So the beauty of the matched filter allows you to make decision in this noisy signals. And you can see that the output of the matched filter is much easier to deal with. Now let's summarize. In the presence of noise, in the presence of white noise, the output, the optimal output, in the presence, of course, of white noise, additive white noise with zero mean, with some restrictions, the optimal matched filter, the optimum is a matched filter which has the following impulse response: scaled, inverted, and delayed version. And we have also the frequency domain response. That's the frequency domain of the matched filter. We also know that the output will always be less than or equal to this value, where this is the energy of the signal. The max exactly will be 2e over n naught. We also learned that the exact shape of the pulse does not affect the performance, but rather how much energy is in the signal. I have shared the following example with you. And now it is time to look at the block diagram, which we have seen. For the special case of rectangle, we can say that the matched filter is nothing but integrate and dump, a constant integration and dump. Remember that this is an example of a matched filter where we flip the signal and then shift it to the right by an amount of t. Okay, so this is basically the matched filter performance. We'll talk about it more in future lectures. Thank you for being good listeners, and we'll see you then.